Hey everybody, this is a video on standing waves. Standing wave is one of the most common kind of wave phenomenon that we see, and it's a combination of some simpler wave phenomenon. But anytime you hear a note on a musical instrument being played, you're hearing a standing wave, or it's created through a standing wave in the musical instrument, whether it's a standing wave on a string or a standing wave in some sort of tube. So standing waves are all over the place, and we can see a diagram of one here. If you look at the red line, that shows us a standing wave pattern. The green wave is traveling to the left, the blue wave is traveling to the right, but the red wave looks like it's not really moving at all. It's just kind of vibrating back and forth. That's a standing wave. And a standing wave, this pattern is what we get when we have one wave traveling forward and one wave traveling backward, and they're the same frequency, therefore wavelength, and amplitude. And if they're the same frequency and amplitude, we get, basically they interfere with each other, but in some locations they're going to interfere constructively, causing it to be this kind of vibrating bulge thing. And in some locations, they're going to interfere destructively, which causes the wave to always cancel out. And so the shape that we see is the product of that interference, and we call it this standing wave pattern. Standing waves still have wavelengths, they still have frequencies, and they still have wave speeds, but the wave speed is going to be the speed of the traveling waves that are kind of combined to make them. And so in practice, the way we get a standing wave isn't by taking two equal waves and sending them back against each other. What happens is if you send a wave of a specific frequency down a medium, when it hits the edge of the medium, it's going to reflect back with the same frequency. And so that reflected wave interferes with the, we say, incident wave, causing our standing wave pattern in red. And we can see this here as well. We have a right-moving red wave and a left-moving blue wave. When they're exactly aligned on top of each other, we would say in phase, or when they're on top of each other, when their crests are aligned and their troughs are aligned, we get constructive interference everywhere. So we get a very large wave shape. But as they pass by each other, they get a little bit out of sync. And so we get some places where we cancel a little bit more, and some places where we, everywhere just kind of cancels a little bit more. And then when they're fully out of phase with each other, our wave is totally canceled, and so we'll see our string as being totally flat for that moment in time. And as they continue to pass by each other, we'll get constructive interference in the opposite direction. But one thing you'll notice is that at these little dotted lines, the blue and red waves are always exactly opposite each other. So we always get destructive interference there, which means there's no vibration of our medium. These longer dotted lines, these dashed lines, blue and red are always on the same side of each other. So we get constructive interference. And it vibrates between positive and negative constructive interference. But that's where we get these bulges that vibrate back and forth. The locations where we get destructive interference, where the medium does not move, it's called a node. There's always going to be a node if your medium cannot move at that particular location. So nodes can form because of the interference, or if you just hold on to your guitar string, for example, you're going to get a node at that point. The locations where we get constructive interference are always halfway between the nodes, and they're called antinodes. They're going to be the maximum amount of constructive interference. They're going to be where we see these bulges here. Also notice that in this diagram, we can count the total number of wavelengths on our standing wave. Here we have 1, 2, 3 nodes, 1, 2 antinodes. But if we actually measure out the waves, we have one full wavelength. Which means to go from a node to another node, that's only going to be half of a wavelength. And we can use this, we can basically just use the diagrams we draw to figure out the wavelength of our standing waves. So here is that animation again, and I just want you to take a minute to look carefully at the antinodes and nodes. The antinodes are going to be these locations of maximum displacement. We can see blue and green are always on the same side there. The nodes are the locations where their medium doesn't move at all. So the red rope, the resultant wave, is always at 0, and blue and green are always on opposite sides. This is going to be for waves on a string, and I'll elaborate more on different types of waves in a few slides. But this concept applies to anything. Or to any standing wave. We can only get certain frequencies and certain wavelengths of standing waves in a particular medium. It depends on the shape of the medium. It depends on the type of medium. But we're only going to be able to get certain frequencies of standing waves. The lowest frequency we can get that creates a standing wave is called the fundamental frequency, or the first harmonic. This is important for musical instruments because the first harmonic is going to be the pitch of the pitch that you hear, the main pitch that you hear on any musical instrument. So that would be the pitch that your instrument is tuned to. So for a guitar string, the first harmonic is going to look like this. It's fixed at both ends, so we have a node at both ends, and we have an antinode right in the middle. We count the number of waves. There is one bulge, one antinode, which means we have half of a wavelength there. The first harmonic is actually let me go back. Since the first harmonic is the lowest frequency that we can fit, it's the largest wave that we can fit. We're always just really, when we do standing waves, we're going to try and draw our pictures such that our wave just fits in the medium. On a guitar string, we can only fit a wave in if both ends are nodes. Which means if we start on our wave shape, we're starting at equilibrium. So the other standing waves that can form in a medium are called the other harmonics. And they're always going to be integer multiples of our fundamental frequency. And we can kind of see that here. Here we have half a wave, so I'm going to write lambda over 2. And here we have one full wavelength, 1 lambda. And here we have 1.5 lambdas. I'm going to write this as 2 lambda over 2. This is 3 halves of a wavelength. So we can see that we're dividing our wavelength. This is half of our original wavelength. This is 1/3 of our original wavelength. This is 1/4 of our original wavelength, which means that this second harmonic is going to be twice the frequency. Half the wavelength is twice the frequency. This is 1/3 of the wavelength, so it's 3 times the frequency. And so we can write an expression for the frequency of the nth harmonic. F sub n is the frequency of the nth harmonic. It's just n times the frequency of the fundamental, or n times the frequency of the first harmonic. The second harmonic is always twice the frequency. The third harmonic is always 3 times the frequency, etc. If we want to figure out the wavelength, or the wave speed, well, we might need to figure out the wavelength. We just use the diagram. If we know the length of our medium, or the length of the string, let's say it's L, then for our first harmonic here we have half of a wave. Just look at our wave shape. This only goes half. Full one would have to come back up. Our second harmonic is 1 full wave. Our third is 1.5 waves. So we can create a little equation we could solve for lambda if we wanted in terms of L. That way, if our length is, let's say, 10 meters, then that means our lambda here would be, well, lambda equals 20 meters. Here, lambda equals 10 meters. Here, lambda equals, well, it's going to be 6.67 meters, etc. We can just look at how much space one full wave takes up. But you have to draw the pictures. So, and that's generally going to be our strategy for working with standing waves. We're going to draw the pictures of the harmonics. Then we'll use the length of the medium and wave shape to find the wavelength. If we need to use the harmonic number and the frequency, we can do that. We can also use our wave speed equation as necessary. That's wave speed equals lambda f. This still applies even if we have a standing wave, because our standing wave is made up of two traveling waves. I just went through how to calculate the wavelength, so I'm going to skip forward. So all the diagrams before showed us standing waves on a guitar string. And they always have that same shape where the ends are kind of fixed and they vibrate in these kind of different numbers of bulges, different numbers of antinodes. But that's because of the guitar string itself. And in fact, it's the boundary conditions that determine the shape of the standing wave. Both ends of our guitar string were fixed, which means that we had to have nodes on both ends. Well, if one end was free, then that would mean we would get an antinode at that end. So a fixed end of your medium creates a node, and a free end always creates an antinode. Sometimes we might have one end fixed and one end free. For example, if there is a telephone pole. Now, we don't often think of waves forming in a telephone pole, but they can. And they do, and you can get standing waves. This is a free end. This is fixed. So we'll get a node and an antinode here. Node, antinode. We still are going to fit the smallest waves we can into our medium. But since we're going from node to antinode, sorry, that was the largest waves we can. Node to antinode, that's from equilibrium to the next crest. Well, then our next wave, so that would be our first harmonic. Our next wave, well, it still has to go from node on one end to antinode on the next end, which means it's got to go from here to here. So our next wave looks a little different. And in fact, our wavelength is 1/3 as much as our original wavelength. So this is actually going to be our third harmonic. Now we can figure that out because the wavelength is 1/3 as much, so the frequency is 3 times as much. But it's just a weird quirk that if we have one end fixed and one free, there are no even harmonics. We can also get standing waves out of longitudinal waves, although we still usually diagram like transverse waves. And this is going to be any wind instrument. Pipe organs create standing waves out of pipes. And essentially, there's a longitudinal wave that gets sent out, and it reflects at the end of the pipe. And so we get places where constructive and destructive interference, we get these particular standing waves, and we get different tones. If you've ever played a pipe organ or an organ, you can sometimes change you can close the tops of the pipes, you can change stops to change the tone. That's because you're just changing the shape of the medium and changing where these nodes and antinodes are. The boundary conditions for sound waves are going to be kind of similar to transverse waves. If we have a pipe that has an open end, if it's open on one end, then the air is free to vibrate on that end, which means we have an antinode. We have a pipe that's closed on one end, there's a wall there, which means there's no vibration, it's going to be a node. We could also have a pipe that's open on both ends, it's like a tube. That would just be two antinodes. So let's look at the wave shapes for when we have different types, standing wave shapes. So here's actually all the different types of standing wave shapes. If our pipe is closed on both ends, then we have to have a node and a node, which means we have, if we think about our wave shape, we're going from this point to this point. So we get half a wavelength. That length is lambda over 2. Our second harmonic, we get a whole wavelength, lambda, and then this is 3/2 of a wavelength, so on and so forth. If both ends are open, then we just start on antinodes. So we're starting here, and we'll go to the next antinode, the next crest. So it's going to look like going from the top down to the bottom, and kind of vibrate like that with our node in the middle. Node, antinode, antinode. We still have half a wavelength here, because we went from crest to trough. This is going to be lambda over 2. Here we have a full wavelength because we went from crest to crest, lambda. And here we have one wavelength and 1/2 wavelength. So 3 over 2 lambda. So if both ends are open or both ends are free, mathematically it ends up being the same. It's only when one end is free and one end is fixed, or one end is open and one end is closed, that we get this kind of weird shape where we skip harmonics. So this is our first harmonic, second, third. And then for our half open, half closed, this is our first, third, and fifth. So let's do some examples. The student wants to measure the speed of a wave on a pole. The 2.0 meter vertical pole is erected so that its base is on the ground but the top is free. A variable frequency oscillator is placed at the top of the pole, and the frequency is increased until a standing wave pattern appears. The frequency at which this occurs is 0.75 hertz. 1. Draw the standing wave pattern. Okay, so we know that our pole is fixed at one end, and it's free at the other end. So that means we're going to have a, let's just say it goes pole of height h. So if it starts as a node and if it's free at the other end, it's going to be an antinode. So our first harmonic is going to look like this, maybe something like this, if we were to kind of sketch that out. Okay, so number 2, calculate the wavelength of this wave. Well, we know this height is 2 meters. And how much of a wave do we have here? Well, a full wave would be node to the next node to the next node. We only have node to antinode. That's a quarter of a wave. So 2.0 meters is equal to lambda over 4, or lambda equals 4 times 2 is 8.0 meters. Okay, cool. Number 3, calculate the speed of the wave in the pole. So the wave is going down the pole, it reflects on the ground, goes back up, which causes this vibration pattern. And we'll just use wave speed equals lambda times f. We know the wavelength is 8.0 meters. We just measured it. And the frequency is 0.75 hertz. So we just need to multiply those two together. We get 6.0 meters per second. Transverse waves don't travel very fast through medium. And then 4, determine the next standing wave that will occur if the frequency is increased. Well, to do that, I'm just going to sketch out again what we have. We have a node here, and we have an antinode up here. So I'm going to try and add a half wavelength, and it's going to look like that. If I did it the opposite direction, it would look like that. So that's going to be the third harmonic. We can't have the second harmonic because the second harmonic would have a node at the other end, and it doesn't have a node at the other end, it has an antinode. So let's try another one. A guitar string is tuned to have a wave speed of 880 meters per second. Draw the standing wave pattern on the guitar string. It should say for the first harmonic. How long must the neck of the guitar string be in order for this string to play a 512 Hertz note? Okay, so let's draw the pattern. We have a node and a node. And it's the fundamental frequency, so it's just going to look like this, which means we're getting half of the wavelength. L equals lambda over 2. For the full wavelength, we would need 2 antinodes. I know this drawing's kind of bad. How long must the neck of the guitar be in order for this string to play a 512 Hertz note? Well, what are we given? Whoops. We're given the frequency we want is 512 Hertz. We're given the speed is 880 meters per second. So we can figure out what the wavelength needs to be. Lambda equals, from the wave speed equation, it's just going to be speed over frequency. So 880 over 512. 1.72 meters. So if our wavelength has to be 1.72 meters, and L is equal to lambda over 2, because L is the length of the string, we'd say L equals 1.72 meters divided by 2. Equals 0.859 meters. 0.859 meters. Is how long our neck needs to be. Okay, find the frequency of the second and third harmonics of this note. Well, we know that the frequency of the nth harmonic is just n times the frequency of the first. So the frequency of the second harmonic is just 2 times 512 Hertz equals 1024 Hertz. And the frequency of the third harmonic is 3 times 512 equals 1536 Hertz. By the way, these harmonics have important meanings in music as well. The second harmonic is 1 octave above a note. The third harmonic is, I believe, an octave and a fifth above your note. The fourth harmonic is 2 octaves above your note. Okay, question 3. A speaker is placed at the end of a 0.45 meter tube that is open at both ends. If the speed of sound in air is 330 meters per second, draw the standing wave pattern for the first 3 harmonics and determine the wavelength and frequency of these harmonics. So we have a tube. The length is 0.45 meters. And we want to find the first harmonics. Since it's open at both ends, we're going to get antinodes, which means I start with a crest. I'm going to go to a trough. It's my first harmonic. Second harmonic, I'm going to go crest to trough to crest. See if I can do that. Third harmonic, crest to trough to crest to trough. So it's kind of hard to draw like that. And often we'll draw it both ways. because it is going to vibrate back and forth. Okay, so this is n equals 1, n equals 2, n equals 3. Determine the wavelength and frequency of these harmonics. Well, here I have 0.45 meters is equal to, how many waves is this? That's half a wave. So lambda over 2, which means lambda equals 2 times 0.45. So 2 times 0.45 is 0.90 meters. Here I have one full wave here, so 0.45 meters equals lambda. Well, that's just it. 0.45 meters equals lambda. Lambda equals 0.45 meters for symmetry. Here I have 1.5 waves, so 0.45 meters equals 1.5 lambda. So our wavelength is 0.45 meters over 1.5, which is just 0.30 meters. To find the frequency, we can just use our wave speed formula. Speed equals wavelength times frequency. And if we solve for frequency, we get F is equal to V over lambda. So we can just plug in our numbers up here. F of our first one is equal to our wave speed, 330 meters per second over 0.90. Which is 367 hertz to 3 sig figs. Right here we get 330 meters per second over 0.45. .733 meters per second, twice the frequency for the second harmonic. And the frequency of our third harmonic should be 3 times the frequency, but let's just check it anyway. 330 over 0.3. Oh, and these should be hertz, not meters per second. 1100 hertz, 3 times our original frequency. So that's that. In summary, standing waves are produced by reflection and interference of waves in a medium. Only specific frequencies called harmonics produce standing waves in a medium. Nodes and antinodes are locations of destructive and constructive interference. Boundary conditions determine if there will be a node or antinode. Harmonics are the standing waves that form in a particular medium, and they depend on the boundary conditions, always integer multiples of our fundamental. But our main takeaway is we need to know what the standing waves look like, or at least figure them out by drawing pictures, and then we use the pictures, we use our wave speed equation to solve problems. Thanks.